Guys, this is Professor Janacek. I want to go over an application of vector-valued functions. Let's take a look at arc length. To begin with, let's let r of t be a vector-valued function defined with components f, g, and h. Here I'm calling it an oriented curve, meaning it's a curve with going in a certain direction. And I also want to make sure that f prime, g prime, and h prime are continuous on the interval ab. Now, I'm not going to go into the derivation of this formula, but to determine the arc length, we have a formula for that. It is the integral over the interval AB of the square root of f prime of t squared plus g prime of t squared plus h prime of t squared. Which, by the way, is the integral of the magnitude of the derivative of r. And there you go. That's how we find arc length. Let's take a look at some examples. To begin with, let's find the length of r of t defined by t squared over 2 for the first component and 2t plus 1 to the 3/2 over 3t for the second component, and we'll look at this over the interval from 0 to 2. Well, let's see. First off, we will go ahead and give our components their names. F of t is t squared over 2, and g of t is 2t plus 1 to the 3/2 over 3. From there, we can get f prime. Simply the power rule gives us t. And g prime, let's see, we have the power rule. And I don't have that one in there. There we go. We have the power rule, but we also have the chain rule. So with the power rule, we'll be able to reduce the 3. And then the chain rule will allow us to also reduce a 2. So that gives us 2t plus 1 to the 1/2 power. Take your time on that. Again, power rule and chain rule in this one. All right, so what about the arc length? The length of that curve is going to be the integral from 0 to 2 of the square root of f prime squared plus g prime squared dt. Well, I don't think this will be too bad. First, let's square each of these functions. Well, that wasn't so bad. That worked out quite nicely with that 1/2 exponent. And it looks like here inside this radical, that factors to t plus 1 quantity squared. Oh, isn't that lovely? By the way, don't forget to write that dt, that differential there at the back is very important. But look at this, how lovely. The square root of t plus 1 squared, we end up with just t plus 1 in our integrand, which is quite simple to integrate. That gives us, 1/2 t squared plus t evaluated from 0 to 2. A quick computation. And it looks like, what is that? 2 plus 2 gives us 4. All right, not so bad on that one. Let's take a look at example 2. We want to find the length of the curve r of t defined by the components 4 cosine t, 4 sine t, 3t for t going from 0 to 6 pi. All right, to begin with, again, we'll define f of t as 4 cosine t. G of t, we'll let that be 4 sine t. And finally, h of t is 3t. From there, we'll find f prime of t, which is negative 4 sine of t. G prime of t is 4 cosine t. And h prime of t is simply 3. Notice again here, I'm taking the derivative at this point. But now I'm going to set up an integral. So for the length of this curve, we're going to integrate from 0 to 6 pi. The square root of f prime squared plus g prime squared plus h prime squared. Now let's see, oops. That gives us the square root of 16 sine squared t plus 16 cosine squared t plus 9 dt. Well, this looks like it's going to work out nicely as well. Let's see, I can factor out the 16 sine squared t plus cosine squared t. That's going to be just a 1. So we end up integrating from 0 to 6 pi of 25, the square root of 25, which is just 5. So when we integrate, we get 5t, and we'll evaluate that from 0 to 6 pi. A real quick computation here. And it looks like we end up with 30 pi. Well, there you go. Enjoy.